let's get started. First of all, any questions about anything from last week? Last week we were dealing with the graph traversal problems. How many people got all four of the graph traversal problems? Okay, 3. How many people? 4. How many people got 3 of the graph traversal problems? Okay, good. How many people got 2 of the graph traversal problems? How many people got 1 of them? Unfortunately, we don't have those people aren't here yet. And how many people got 0 of them? Okay, anything interesting in any of the graph traversal problems to talk about? Okay, that come to mind here that anyone found interesting one way or another? Okay, let's get in. This is another isolated one. How many of the graph traversal problems did you get? How many of the graph problems from last week did you get in? 2. Okay, fair enough. Okay, let's talk today. I want to continue talking about graph problems, but I want to talk more about graph algorithms, what I would call graph algorithms. I'm going to break the graph world into 2 kinds of problems. One that you can basically solve just by doing a traversal, okay, in the right way. The other of which requires sort of higher order concepts in graph theory. And I'm assuming everybody here has had a reasonable amount of graph theory. Like I say, to me, the key thing to do in solving a graph theory problem is to find the name of what your problem is. Okay, and then figure out how to format your problem into the algorithm that already exists for it, basically, rather than designing your own graph theory algorithms. This is what I have found is the case. There's a thing called modeling. I mean, the bigger question is a question called modeling. The question is, how do you model your problem as a graph problem? And graph theory gives us a language to talk about many different things. So let's go through. I'm going to try to zip through a certain amount of a lot of graph algorithms today. But I would prefer it actually if people stopped me if they found things that were interesting and slowed me down, because I noticed I have too much more than really should be covered in a day. But so we'll see what happens. But the first notion of which we talked about a little bit before, of a property of graphs is connectivity, okay? And the question of whether graphs are connected let's power this off before I get into the question of whether or not a graph is connected, or how connected a graph is. There's several different issues involved. First thing we talked about was whether an undirected graph was connected. That got into the issue of connected components. And that is basically a traversal problem. When we talked about how strongly a graph is connected, this gets into a different set of questions. Okay? So the classic example would be, if you were a terrorist, okay, and you want to disrupt the phone network. Here is the phone network. Where do you plant a bomb to disrupt the phone network? Okay? If anybody takes a look here, what would be the obvious place to plant your bomb? Okay? It would obviously be here, because this would have the property of preventing anybody on this side from talking to anybody on that side. Correct? So, we say that a graph, a vertex whose deletion disconnects the graph, that is called typically an articulation vertex, okay, or a cut node. Okay? Sometimes there is a edge whose deletion will disconnect the graph. Notice that this graph, in this graph, there is no edge whose deletion will disconnect the graph. There is a vertex which will disconnect the graph, but not an edge, right? If we go and we add another component here, perhaps. Here we have a world where now there is an edge whose deletion will disconnect the graph, right? We call an edge whose deletion will disconnect the graph a bridge. We call the vertex whose deletion will disconnect the graph a cut node. Okay? Obviously, any vertex that is adjacent to 2 cut nodes, okay, disconnects the graph. But it's not clear. Is it clear that if you have an edge, both of whose vertices are cut nodes, is it necessarily a bridge? Let's think about this for a second. Here we've got in this graph now, there are 3 cut nodes. There is 1 bridge. Clearly, if you have an edge whose deletion will disconnect the graph, then the 2 endpoints of it are both cut nodes. Because when you delete that vertex, you delete that edge for free. Actually, is that true? What about in the case of a tree? Let's take a look at this thing. Here we've got an edge, okay? This edge is a bridge, am I right? Its deletion disconnects its graph. Is this a cut node? The answer is no, right? So it's not even true that both endpoints of an edge, of a bridge are cut nodes, okay? In general, we would like to think that's true, right? Even if a vertex has both edges that are, are cut nodes, that does not mean that the edge between them is a bridge. If you look over here, we have a good example of this, right? So both of these are cut nodes, but this edge, deleting that edge does not actually disconnect the graph. Any questions about this? So there are notions here, when we talk about undirected graphs, of vertices whose deletion will disconnect the graph. There are edges who will disconnect the graph. Any questions about that? How do we find out if there is one vertex whose deletion will disconnect the graph? We talked about that last time. What is the easiest way to do that? What? Basically repeated what I will say breadth first search, right? I guess what you would say is if you wanted to find out if this was an articulation vertex, the easiest thing to do was to delete it from the graph and then do a connectivity test, right? What about testing if an edge is a bridge? Say delete the edge and test it, okay? So we agree that in both of these problems, doing the test of any particular edge or vertex is a edge or is a bridge or a an edge of a bridge or articulation vertex can be done in one traversal. If you want to naively find out if there are any articulation vertices, you can do this n times, one for each vertex. If you want to test if a graph, an edge is a bridge, okay, you can do it. You'll find out if there are bridges, you can do this m times. One for every edge in the graph. Delete it, see if it's still connected. Any questions about that? Now, for all of those problems, there are in fact faster algorithms based on one depth first search. We sort of hinted at this a little bit when we were talking about depth first search last time. In general, if you want to tell whether a vertex is an articulation vertex, this vertex would be if none of the descendants of these, when you do a depth first search, everything became a tree edge or a back edge. If none of the ancestors got above here, that would then mean that this is an articulation vertex, right? Under what conditions is this edge a bridge? Okay? It would be if none of, let's just think about it. First of all, the edge would have to be a tree edge, okay? And it would have to be the case that none of these ancestors got above here. Notice that a vertex can be an articulation vertex if one component of it is severed off. An edge will be a bridge if and only if the whole subtree below it is severed off. So all of these can be done by sufficiently clever, backtrack, clever use of depth first search. Any questions here? But of course, in a contest situation, they probably don't expect you to do clever depth first search because it takes time to get that thing right. Any questions?
So you can see the root when you find the cut.
What?
The root.
Oh, the root. The question now is, under what condition is the root a cut node? Oh, is that what the question is? The root is going to be a cut node if and only if its degree in the depth first search is higher than 1. Notice that, that if you've got a vertex here, okay, if a vertex, if you have a root, the root can't be a cut node, okay? If it's only got, let's say, one edge coming off of it, then it's going to be basically a leaf. It doesn't sever anything. The only way that a root can be a, cut node, is if, in fact, it's got a degree of 2 or more in the depth first search string. Does everybody see that? Because somehow, if it had a degree of depth, a degree of 2, that meant that after you explored all these vertices, only then you discover this when you're exploring the root again. That meant that there was no way to this root, to this node, except through the root, because if so, it would have been discovered down then. Any questions about that? Okay? So the details, I would be hard-pressed to come up with the details of this, okay, as I was programming it. Okay? But in principle, you should believe it can be done in linear time, but you have to. Okay? Any questions? And if not, I would do the brute force test and all. Any questions? Actually, there's one other notion of connectivity, which I'm going to hope to get to by the end of class, but maybe you haven't seen before. I know many of you have probably seen this notion of connectivity, which would be supposing. Here we have a terrorist with one bomb trying to disconnect the graph. What if, on the other hand, we had a well-funded terrorist, okay, who could possibly buy a lot of bombs, okay? Suppose I now give you this graph, and our terrorist now wants to disconnect it using the smallest number of bombs, okay? This is another notion of connectivity, right? Before one bomb sufficed to disconnect it. What's the smallest number of bombs that we have this one defined properly? Let's just take a look at it. What's the smallest number of bombs to disconnect this graph? Okay? 2. I would argue 2 will disconnect it. Basically, take this bomb and this bomb, right? That's 2, right? That then, of course, in some sense, that's given by the degree of this vertex, right? But what if we had another edge like this? Okay? Still 2. Where's the other one that's 2? Lower right corner? Lower right. Well, it turned out there was also an edge from here to here. So how would we find the smallest number of bombs to disconnect the graph? Okay? This may start to seem like a much harder problem. Okay? We agree that if there's one bomb to disconnect it, that was actually a depth first search connectivity testing thing. What if you want to find the smallest number of bombs to disconnect the graph? Can anyone give me a slow but correct algorithm for this? Okay, so you're not using something, okay, you're saying try the minimum cut between every pair of nodes. You're using network flow for that, right? Okay? The interesting thing is there's a way to do this using network flow. But for those of you who don't know about this, how many people here don't know much about network flow? Okay? Undergraduates shouldn't know too much about network flow, although maybe you do. Some of you who are programming contest teams probably do. Okay? The interesting thing, this is a good example of a problem where a network flow solution exists, where otherwise it would seem very, very hard to do. Okay? We haven't talked, maybe we'll talk about network flow at the end of class, if I get that far. Maybe we'll go and revisit it. How might you do it without network flow? If you want to find the smallest subset of vertices whose deletion will disconnect the graph. What would would be the simple but perhaps slow algorithm for it? Okay? We live in a world where network flow doesn't exist. What would be a simple but slow algorithm for that?
Not necessarily polynomial.
Not necessarily polynomial. Okay? Let's start out with that one.
Try every set of the subset of the vertices.
Try every subset of vertices and see if that severs the graph, right?
Binary search for the answer.
Well, you would say binary search for the answer. That might be, so that's a refinement for it. You're trying to say that instead of try all subsets total, you try all subsets of size 1, then of size 2, then 4, then until you hone in on the size. Is that what you're saying? Okay, that would be true. Another refinement would be to use the fact that you know that the lowest degree vertex gives you some kind of an upper bound on it, right? In this graph here, there is a low degree vertex of degree 3. Clearly, 3 bombs will suffice, okay? And so you don't have to go all the way up to n. You can stop at that point, okay? Or start from that point and work down. Any questions? Okay? So connectivity is an interesting problem and an important problem. And like we'll say, one of the examples of why network flow is a good thing, in case we get time to talk about that very much. Any questions? Okay. We also talked about directed last class. There's also notions in directed graphs of strong connectivity and weak connectivity. Namely, we would say that a graph was strongly connected if there was a way to legally drive between any 2 places in the graph. Okay? If I could always drive from here to there for every notion of here and there, then the graph was strongly connected. If on the other end, there was we lived in a world where, let's say that there was a, what you call it? We had a graph that looked something like this. You could legally drive from here to there, but you could not legally drive back. Does everybody see that? Okay? This would be a graph that's weakly connected but not strongly connected. Okay? And the obvious ways to determine that, again, involve search, naively using search, or more cleverly. So we sort of talked about that last class. Any questions about weak connectivity or strong connectivity? Okay? I'm happy to be slowed down for that if people would like to talk about that again. Okay? Any questions? Okay. One of the other major graph theoretic things that you learn about in a graph theory class has to do with cycles in graphs. Okay? What is an Eulerian cycle? How many people here have heard of Eulerian cycles or Euler cycles? Okay? What are they? They're cycles with what property? Given a graph, they visit every edge exactly once. Does everybody see that? So here, if we take a look at this graph, let's say it's something like this. Here is a graph now. These are my vertices. Is this graph have the property that I can start from one place, visit every edge, and end up back where I started from? Okay, the answer is say no. Why is the answer no? Odd degree.
On degree. No, you have to prove on degree.
You look at this thing, let this, so I guess I made it uglier than I should have. We get rid of this edge. Suppose we don't have this edge in it. Okay? Is it possible to start from any place, visit every other vertex, and get back to where I started from? The answer is yes. Let's try an example here. Let's say I start from here. I might as well go there. Where should I go next? Anybody have any preference?
Anywhere.
What?
Anywhere would be.
You say I can go here, anywhere. Maybe I'll go, but where did I start from? Here, right? I have to end up here again, right? Here I can now go from here to here, to here. Does everybody see that? So an Eulerian cycle, okay, that's what I mean by Euler here, named after the guy who developed it. Eulerian cycle is one that visits every edge of a graph exactly once. What kind of problems might Eulerian cycles come up in? Can anybody come up with an example of a problem where someone in the world might want to solve a problem? Where you give it a graph, visit every edge in the graph. What? Okay, so the classic example of it is the 7-bridge problem. But that's not really an application. That is something that originally Euler, when he was thinking about this, he was looking out his window. In his town there were a bunch of bridges. Okay? And he wanted to know if it was possible to walk, to visit over every bridge exactly once. Okay? Now that problem got solved in World War II because actually in the town they blew up all the bridges. And now you can't do that. Okay? But a bigger question is what is an application where people might pay money for it in theory? Okay? Maybe if you're a tour guide in Euler's town, you would care about being able to walk on all the bridges. But what would be an application where someone would care about? What?
Salesman.
Salesman problem. Why would a salesman want to visit every edge of a graph? What would be the graph? And let's think about this from a modeling point of view. Okay?
The agents are the roads and the vertex are the cross points.
Okay, so now you've got a road network with junctions. Now, why would someone want to visit every road exactly once? Is that a salesman?
Yeah, to do the promotion.
So you're saying that, I see, you've got a sales truck, for example. One application might be, you've got one of these trucks that scream out messages. I don't know if there's anybody, do they have those in Hong Kong? Where you have what do you call it? A speaker on the back of the truck saying, shop at Joe's. Okay, eat at Joe's restaurant. Okay? If you had a truck like that, you might want to visit every edge of the graph, right? To make sure every house has been exposed to it. What would be another example of an application where you might want to visit every edge of a graph? Okay? I would say street cleaning would be an example that I would think about. Okay? If you want to clean all the roads in a town. Okay? Or where I come from, they have snow plowing. Right? There's snow. People know about snow. Right? It accumulates on the roads where I am. Okay? And so they send out machines called snowplows. Okay? To clear all the roads so people can drive. Those people, to try to maximally efficiently use one of those, the snowplows. Basically, they want to solve something that looks like a Eulerian cycle problem. Any questions about that? Okay? So how do you test whether a graph is Eulerian? This much I think everybody knows, right? How do you do it? Somebody here. Test whether or not a graph permits such an Eulerian cycle. What do you need?
I think there are two conditions. First, the graph must be connected.
It's got to be connected because if not, here's a world where there's clearly no way of doing it, right? So it's got to be connected, and what else?
The degree of each vertex is even.
The degree of every vertex has to be even. Now, why is that necessary? Let's think about why it's necessary. What? It's necessary because somehow, if you're starting at some place, you've got to leave and come back, right? Every time you leave, you've got to come back. And if you're not allowed to use edges anymore, that's going to be an argument that it has to be, that you need an even number of degree. Okay? It's not clear it's sufficient, by the way. Okay? But it should be clear it's necessary. So testing whether a graph permits you to visit every edge exactly once in an Eulerian cycle. That one should be pretty obvious, right? You sum up the vertices, see if its degree is even. Test if it's connected, because that's also important, right? But that we know how to do. Now I have something different. How do you up with the order of what edges to visit so as to make this work. I think we decided this was the ordering that I used, right? How can you now find the ordering of edges on an Eulerian cycle? Okay? Any ideas about doing this? What?
Order doesn't matter.
You say order doesn't matter. It matters to the guy driving the truck that's going to be cleaning the streets, right? He needs to know where to go. And it's not clear to me, what do you mean by that order doesn't matter? Okay? I don't really believe that that's true. Does everybody believe? Let's see whether he's right. You're sort of saying, if we say order doesn't matter, you want to say I can start, if the graph has the right property, you're saying I can't make a mistake. Okay? That I just keep walking to some edge that I haven't used. Okay? Anybody kind of counterexample to that?
Only if you have two or ordered vertices, then you have to start with one. Otherwise, you just won't.
Okay. What's your example?
If you start from the top,
Okay. Actually, but I think what you're saying is something like this, for example. Okay. If I start from here, see, I can go wrong. 1, 2, 3. Oops. I'm now trapped, right? So it's definitely not the case that I can go and walk in any direction. Did you add some kind of a correction to this algorithm, if I'm correct? Right. What was that? Or you now retract that? So how do you actually find the torque? Can anybody suggest a convincing way to find the torque here? What?
Depth first search.
And depth first search, how are you going to use depth first search? You say depth first search in post order. Meaning what? You're going to do it in DFS. And what do you mean by post order?
The node, the vertex you receive first is put at the end.
This one is put at the end.
Yes.
But it's the edges that we're going to be doing. I mean, you're not visiting the vertices, you're visiting the edges. So how are you numbering the edges?
It's same.
Okay? So the way that I would do it, there may be a slick way to do it with depth first search. But let me show you my way of doing it that I think is convincing. Okay? First of all, note that if you have a graph where every vertex is of even degree, using depth first search, it should be easy to find a cycle on the edges, right? Look, here's a cycle, right? What happens if I take my edge, my cycle, and I delete it from the graph? What's going to happen to the degree of every single vertex in the graph? Is it still going to be even? It's still got to be even, right? Because I'm taking either 0 or 2 off of every degree, right? So one interesting property is if I've got that breakdown into even degrees, I can decompose the graph into this edge disjoint cycles. Does everybody agree with that? Now, if the graph was connected, though, then by definition, 2 of these cycles have to connect. Does everybody agree with that? And I can splice the cycle, one cycle, into the other cycle to make a longer cycle. Does this make sense? That if I've got a cycle here and another cycle that shares a vertex, I can cruise around the graph like this, then go over here and visit this one before finishing up my job. Does everybody see that? So the way that I would be doing it, I would repeatedly use depth first search to peel off cycles, okay, and then merge them at vertices which they share. Okay? And that, I claim, gives me such an ordering. How many people believe that algorithm? Okay? Now, yes, question. Oh, you believed it. Okay, fine. Okay, any questions? Okay, so that's it. Yeah, question.
I want to ask if all the nodes have the even degree, are you sure have the cycle?
Well, certainly, finding a cycle in a graph, testing whether a graph has a cycle, is a standard breadth first search, depth first search thing, right? How do you test if a graph has a cycle? A graph that does not have a cycle, assuming it's undirected, is a tree, right? So if you did a depth first search, the moment you have a back edge, ding, 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 you have a cycle, right? The tree edges plus that back edge define a cycle, right? I'm now saying rip it off from the graph and start again. Okay? I will eventually be able to, so long as the graph has a cycle, I will be able to find it. And I can keep pulling off cycles until there are no edges left in the graph. Then I claim conceptually I can put these things together whenever I have two cycles that share a vertex. And they must share a vertex if the graph was connected. Does everybody see that? So this gives me a way to find an Eulerian cycle if one exists. Okay? Any questions about that? Now, one other one that's related to it is the other problem is the problem of visiting all vertices in the graph. Okay? Such that there is no, such that you visit every vertex exactly once. And that would be called a Hamiltonian cycle. What would be an example of a problem where a Hamiltonian cycle arises? Okay? When do you want it, or that given a graph visits every vertex exactly once? Mail delivery? I think of mail delivery as actually being like the Eulerian cycle one. At least where I come from, mail, people's houses are on streets, right? So usually when they talk about this, you think in terms of like the traveling salesman problem. That's one where you've got a particular set of places you want to go to, and you want to visit just those places. Okay? Any questions? Actually, think about the Postman problem is interesting, actually, because just for one reason. In the Postman problem, we assume that you've got a postman guy who's driving his mail truck. He has to visit every edge. Note that if the graph is not Eulerian, here we have a graph that's not Eulerian. If the postman still has to visit every edge, they're going to have to repeat certain edges more than once, right? That's a problem that actually, it turns out there is an efficient solution to. And what's more interesting is I want to mention it here. This problem, at least in the United States, is called the Chinese Postman Problem. How many people knew it by that name? Okay? The reason is because actually the guy who first developed this problem was a Chinese mathematician. Okay? So there's no difference between the properties of American postman and Chinese postman. Any questions? Okay? So this is where Eulerian and Hamilton... The trouble is that when you... Finding an order that visits all the vertices turns out to be hard. Visiting all the edges turns out to be easy. Okay? Any questions? What is the difference here, if you had to take a guess? Why one is hard or one is easy? Okay? It's the case really here that you have leftover edges you don't visit. Here you're constrained to visit all the edges. Here you have decisions to make about which edges to use and not use, and that's really where the hardness comes from. Any questions about that? Any questions about Hamiltonian cycles and Eulerian cycles, why they come up, or how to deal with them? Okay, good. Okay. When you take your graph algorithms class, there are a few algorithmic problems on graphs that are always covered. These are minimum spanning tree and Dijkstra's algorithm, shortest paths. How many people here have seen Dijkstra's algorithm? Raise your hand if you have. Raise your hand if you have not seen Dijkstra's algorithm. Okay? It's okay to raise your hand. Okay, good. So these are problems on weighted graphs. Okay? Because the problems on unweighted graphs tend to be easy. A spanning tree of a graph is a subset of edges forming a tree connecting all the vertices of a graph. Suppose, let's say, I gave you an unweighted graph, and I want a spanning tree. How do you find a spanning tree of an unweighted graph? Depth first search or breadth first search? Does everybody agree with that? The discoveries will form a spanning tree. So finding a spanning tree is no big deal. If you've got weights on edges, okay, what comes up to be the important problem is that of a minimum spanning tree, which is a spanning tree whose sum of edges is as small as possible. Okay? Why do people care about minimum spanning trees? Let's think about this. Okay? Given a graph, under what might be an application for a minimum spanning tree? Okay, can anyone think of weighted graphs in the world where you might care about minimum spanning trees? Okay.
Low, for example, low construction to break the city connecting.
Okay, so you live in a world where you have people living here, and you now want to build a road network for them, right? You want to make sure that everybody can go to everybody else. This can be done by you need a spanning tree. Certain spanning trees are better than other ones, right? If the goal is to minimize the cost of connecting the roads, right? What spanning tree do you do? If the weight of the edge is the cost of building the road between it, then the minimum spanning tree is the cheapest way to build that road. Does everybody agree with that? What if you are a corrupt official in this town and you want to build the road network that connects everybody while making yourself as perfectly content as possible? What would be the road network that you would use? If this is the city, what is the road network that would make you happiest personally? So if I have a freedom, I'm not going to worry about cost. If I had to build a road network that was basically just a tree, what would be the tree that I would want built? Any ideas? What? What if I told you this was me? What would be the best road network from my point of view? Okay? I claim it's the star. Right? So I can go anywhere I want as fast as possible. Does everybody see that? Okay? This would be the best travel point for me in terms of traveling. Any spanning tree is equally good from a connectivity point of view. Okay? If there's a cost associated with it, okay, then the spanning tree, the minimum spanning would be the one of minimum cost. If there is a travel considerations, I would want the one that goes from me to everybody else directly, right? Any questions about that? So minimum spanning trees come up, again, a lot in communication networks because they are the cheapest way to connect by a network or a roadway, all of these other things. Okay? Any questions? So what is the easiest way to do it, or what is my preferred way to do it? There are at least two different algorithms that people have already been taught. What algorithms for minimum spanning tree were you taught? You were probably taught Prims and Kruskal's, right? Of these two, my favorite one is Prims. Okay? Why is that? Well, basically because it's going to be extremely different, similar to Dijkstra's algorithm. And so I find it easier to talk about the two of them, to make shortest paths and spanning trees, very, very similar problems. To represent our weighted graphs, because these are now weighted graph problems and we haven't dealt with weighted graphs before, I am basically giving you my same edge adjacency structure that I used before. Except now, associated with each edge, I've got an outgoing vertex and a weight associated with it. So that's all I really need to do to support weighted graphs. Prim's algorithm for minimum spanning tree worked as follows. You start at one vertex, and then you do what? What's the idea? You start from one vertex. How do you build the minimum spanning tree from it? What do you do next?
Find the cheapest edge.
Cheapest edge, and that guy is now in the tree, right? Does everybody see that? What is the next step that I'm going to do?
In Q.
What?
In Q and updating all the vertex.
Still find the cheapest.
Basically, I'm going to find at all points the cheapest edge that goes from inside my tree to outside my tree. Does everybody see that? I'm going to grow my tree from one point out and maintain it connected as a tree. And the claim is that if I always take the cheapest edge going from in the tree to out the tree, okay, then that will give me a minimum spanning tree. Okay, it's not hard to prove. You saw it in class. Okay, any questions? Now, if we do this in a naive way, the time this should take is n iterations, because we're going to build each vertex once, and at that point we look at all outgoing edges. The naive algorithm would be order n times m, where m is the number of edges. So everybody see that? How do we make it faster than this? What is the idea that we need? Do we have to look at all outgoing edges from here every time we add another vertex to the tree? Okay? The answer is no. What we're going to keep is for everybody who's not yet in the tree. What is the cheapest way to get it into the tree so far? And then when I add this new guy, update all of its neighbors, saying, hey, there's now a way you can get into the tree through me. And if that is less, then I'm going to go ahead and take it. Any questions about that? So this is what Prim's algorithm is going to do. Okay? It is going to keep track of the cheapest edge from the tree to the non-tree for every vertex in the graph. Okay? And iterate and update each time. Any questions about that? The more interesting thing is going to be to look at my implementation here and then compare it to Dijkstra's shortest path algorithm. This is maybe the thing that I think is kind of interesting here. First, I initialize to all vertices that they're not in the tree and that they're infinitely far from getting into the tree. I then start at the first vertex. Okay? While there is somebody who's not yet in the tree, okay, what I'm going to now do is look through all the edges that are, let's just look at this thing. I am now, okay. V is the one that I just am adding to the tree. So the first thing I'm going to do is update the consequences of adding V to the tree. So this is what it's doing for every neighbor of V, for all the neighbors of V. Okay, I'm going to go and see if the edge from V to that neighbor W is less than the current weight. If the current best way to get the W is more expensive than the weight of the edge VW, then I'm going to update that. So distance of W is going to maintain the cheapest way to get there. Okay? Then what I'm going to do is loop through, and for every vertex that's not in the tree, if it's not in the tree and its edge is shorter than anything else that's in the tree, that's going to be my best candidate to add next. And this is my algorithm going to be doing. I'll take the consequences of adding somebody, and then find who's the best candidate remaining. Any questions about that? This, I claim, is now n iterations of where each thing takes linear time. The total time here is n squared. Any questions about that? Okay, so that's for finding the minimum spanning tree. Now, the other algorithm, Dijkstra, it turns out, when he discovered Dijkstra's algorithm, he actually published both Dijkstra's algorithm and the shortest path algorithm, and the minimum spanning tree algorithm at the same time. Okay? He didn't realize, I think, that there was already a Prim's algorithm out there. But Dijkstra's algorithm gives us a way to find the shortest path between any two vertices in an edge-destroyed path. What is the difference between Prim's algorithm and Dijkstra's algorithm? Okay? If we go back to Prim's algorithm here, what is the difference between the shortest path algorithm of Prim's and Dijkstra's? The only thing that differs, okay, as we're going to see, is in this update property. Dijkstra's algorithm is going to compute the shortest path of a weighted graph. We want to find the shortest path, ideally, from a vertex S to a vertex T. In the course of it, we're going to find what is the shortest path from S to everybody. What is the idea here that we need? We're going to start from S and find the shortest path, the edge that is shortest from S, right? The lowest weight edge adjacent to S. And the claim is that if we take the lowest weight edge associated with S, this has to be the shortest path from here to there. Is that right? Is the shortest weight path edge, the shortest weight edge from S to one of its neighbors, the shortest path from S to that neighbor? Is that always true? Let's think about this. Suppose that this is vertex edge has weight 100. This vertex edge has weight 5. Is the lowest weight edge, shortest path from S to X, this path of weight 5? Is that necessarily true? Who here says yes? Who here says no? Okay? The answer is not necessarily. What happens here if I have a path that's of weight minus 98? I give you $98 back for traveling there. And this wedge was weight 1. Okay, maybe I'll give you back $10 for this too, right? Does everybody see that in fact there might be a cheaper way around? Okay, if the graph contains negative weight edges. So Dijkstra's algorithm finds the shortest path between things, but only if graphs don't contain negative weight edges. The argument is that if every weight is positive, then certainly the shortest edge from here to here has to be the shortest path, right? Because everything else just to get out of town is greater than this, right? Has anybody ever had a problem seen a problem where there might be negative weight edges? Okay? Most problems in graphs don't have negative weight edges. Now, can anybody think of a problem where there were negative weight edges? Okay? Or a reason why there might be negative weight edges? Okay? It doesn't happen often, but occasionally it does. One argument would be that if, let's say, you travel this thing, and sometimes they give you you could imagine a world where maybe when you travel someplace, they give you money for traveling here, right? So the cost of going through this node would be non-zero. I fly to Hong Kong. I'm getting paid here in Hong Kong, right? The trip may very well have cost me some money, but my net result for having flown to Hong Kong is positive, right? So that might be an argument that then, if I want to find the lowest cost path from here to there, okay, it might very well be that certain cost paths are going to be negative. Even if they leave me out of the way, the cost will be negative. That would be one example. A better example actually comes in currency arbitrage, actually. And if anybody's familiar with this, but you know that most of the currencies of the world you can trade on an exchange, right? I can convert dollars to yen at a certain price. And I can convert yen to euros at a certain price. And I can convert euros back to dollars at a certain price, right? What would happen if, when I multiplied those things out, I had more money than I started with? Okay? Could you imagine a world where these currency rates are changing a little bit? Constantly. They are constantly changing, right? Unless they were perfectly aligned, it should be possible for me to be able to, at any given moment, maybe there's an opportunity for me to find a way to go convert one to another, to another, to another, to another, and end up with more than I started with, right? There is a way to model that as a problem of finding a shortest weight path on graphs where there's negative weight edges, okay? And so that's a proof that it sometimes happens. Any questions about that? So what's interesting about Dijkstra's algorithm? The only difference between Dijkstra's algorithm and Prim's algorithm that we spoke about were these lines. It had to do with what is the desirability of adding a particular edge into the graph. The desirability, if this was my tree, the desirability of this edge, taking the route from here to there, okay, is a function not only of the weight of this edge, but the cost of getting up to here. In Dijkstra's algorithm, we're looking to build a shortest path spanning tree. The shortest path from this vertex to all the others. The cost of getting from here through this vertex is not the cost of this edge, but the cost of getting to this point plus the edge. So the only things that change is really these lines. Okay, the distance plus weight. If the distance to W is less than, if the best distance I had before is bigger than the distance of getting to vertex V and adding the edge weight, then I would do my updating. Any questions? So Dijkstra's algorithm by this notion runs an n squared time again. Any questions? Okay. Now, the other shortest path problem that comes up, that is actually maybe the simplest one to program quickly in a contest type situation, okay, is a very, very elegant algorithm for solving a more general problem called all pairs shortest paths. Okay? What is all pairs shortest path? Dijkstra's algorithm gave us the shortest path from one source to everybody else. Okay? This is exactly what I was trying to solve when I was talking about me, if I could construct the road network from my house to everybody else. This is what the road network would look like. Right? Now the question is, if I'm given an existing network, if I want to try to find the shortest path from every vertex to every other vertex, that's what I mean by all pairs shortest path. Okay? Given a graph, I'm going to want to build the n by n matrix, telling me what the distance is from vertex I to vertex j. Okay, through this graph. Okay? Any questions about it? I could solve all pairs shortest path by calling Dijkstra's algorithm from n different routes. But there is in fact a slicker way, which is this thing called Floyd's algorithm, which I do want to explain a little more carefully than I did Dijkstra's algorithm. Okay? Any questions? Can anybody think of applications for why I might want to find the shortest path distance between all pairs of graphs, between all pairs of nodes in a graph? Why might I be interested in this? This, I think, is a bigger question than how do you compute it. Okay? Why might I be disinterested in the shortest path matrix, the all pairs shortest path matrix? Can anyone come up with an application for it?
Driving.
What? Driving. So what would it mean? So what possibly I could keep it around, just say keep it on my dashboard, so I could know how long it would take me to get from one place to another. So certainly some maps do include these, at least where I come from. You sometimes do get these maps, these tables, that tell you for all these important cities, how long does it take to drive from one to the other. So I agree, building something like that might be an application. What might be other applications for the all pairs shortest path matrix? Okay? That's for just printing it out. Okay? What would be an application for the all pairs shortest path matrix? Anybody think of something? Why would you want to know it, let's say, in the context of networks, a computer network? Okay? What would the all pairs shortest path matrix tell you? What would, if I gave you the all pairs shortest path matrix for a computer network, where shortest path meant something about transmission time, what would be the interesting thing about that? Okay? It would tell you something about what the longest length of time a message might take. Does that make sense? That if you have something like a computer network, the biggest distance represents the two things that are furthest apart. That would be one way that you could tell. So in a network, one property that people sometimes find is they want to find the diameter of the network. What are the two things that are furthest apart? What two things in Hong Kong are furthest apart? Is it the university and the airport? That's sometimes what I get the sense of. Okay, is there anything else that's further apart? The diameter of what is the longest such thing. That would be readily figured out when you had the all pairs shortest path matrix. What other things might the all pairs shortest path matrix be useful for? Okay, let's just think about this maybe outside the context of it. Why would someone care about all pairs shortest path matrix? Suppose you wanted to draw a picture of a graph. Let's put it this way. You guys can certainly imagine, if I give you a graph just stored as a network, you can certainly imagine making a picture of it by putting dots down on paper and connecting the edges, right? How might the all pairs shortest path distance be helpful for you in trying to figure out how to draw the thing nicely? Any ideas? Where would you want the airport and Clearwater Bay to be on your drawing? The two furthest things that were apart, you probably want them to be far apart on the graph. Does that make sense? What vertex would you want in the center of your drawing? Think about it. If I give you the all pairs shortest path matrix, what vertex would you want in the center of your drawing? Anyone want to propose a candidate for that? So one might be the one that has the average, so you could put the one that maybe has the average, say, since you know now the distance between it and everybody else, you could look for the one with the average distance that's smallest, right? Or you might look at the one that's in the maximum distance as the smallest, right? It's hard to say. I would probably put the one with the maximum distance as the smallest. That's the most centrally located one. Right? So problems of what this all-pair shortest path matrix is tends to come in helpful in drawing graphs, identifying what the centermost graph is, what the most important vertex is, things like this. Okay? So that's why all-pair shortest path is a good problem. Okay? Any questions? Okay? Any other issues? So how do you compute all-pair shortest path? Okay? The algorithm for it is an algorithm called Floyd's algorithm. How many people here know what Floyd's algorithm is? How many people don't know what Floyd's algorithm is? Good. Okay? So Floyd's algorithm is one that works best on an adjacency matrix structure instead of adjacency lists. Every other thing we've talked about here works on adjacency lists usually. But we don't really worry about sparse graphs when we talk about all-pair shortest paths, because by definition the output, if you're outputting an n by n matrix, the fastest you could hope to do it at all would be n squared, right? So we're going to deal with an n by n matrix. And what we're going to do is we are going to use an adjacency matrix data structure for weighted graphs, which is going to keep track of, for every ij pair, what is the weight of that, the edge from I to j. That's basically what our adjacency matrix is going to be. Now, what we want to do is to look at an adjacency matrix with the property that the weights of the values for every vertex pair reflect the cost of traveling there. And this is something that we have to be careful about exactly how we initialize our adjacency matrix. Suppose we live in a, let's say I give you an unweighted graph here. Let's say we have this 1, 2, 3. If this was an unweighted graph, what would the adjacency matrix of it look like? What's the value of 1, 2? We want to write this as an adjacency matrix of an unweighted graph. What would you say that would be? 1. What's the value of 1, 3? 1. What's the value of 2, 3? What? 0? Okay. What's the value, and these are parallel, symmetric, right? Or no, 0. And what's down the middle? What's 1, 1 going to be? That edge doesn't exist, right? So we might say that that's 0. Does everybody agree with that? Now, what if we want this to reflect distance traveled? So we could think about these as distance weights. Suppose, what would be the right way to weight these things? Okay? The weight of an edge, ij, should be the weight of the edge, the travel cost of that edge, right? What is it? Suppose these are 1 and these are 1. We would still get 1, 1 here. What should be the edge weight from 2 to 3 for the travel cost from 2 to 3? What? Infinite. Does everybody see this? That you have to be careful. It really wouldn't have mattered if we declared these to be infinite to begin with, right? For just is the edge present or not present. But if we want to use these to model weights, we're going to have a graph that looks something like this. A matrix where the weight of an element is going to be its edge weight if it exists, and an infinite value if it doesn't exist. Okay? Any questions? So that's what my initialized adjacency matrix is going to do. Okay? It's going to start out by setting everything that's initially equal to, that's not there. Okay? It's going to be set to maxent. Okay? So that the weights make sense. Now, what is the idea of Floyd's algorithm? Floyd's algorithm is an algorithm for all pairs' shortest paths. That's actually very interesting. What Floyd's algorithm is going to do is to keep track of, it's going to define a sequence of matrices. W superscript 0, superscript 1, dot, 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 up to n. Okay? And it's going to figure out what is W sub ij superscript k is going to be what is the shortest path from I to j using vertices 1 through k as possible intermediates. Okay? Let's think about this for a second, because this is actually it's going to look incredibly simple, but it's actually very clever and fairly subtle. Okay? What Floyd's algorithm is going to do is it's going to say, look at the original adjacency matrix in the graph. This is going to give you, if you're only allowed to use the edges of the graph, that is going to be the shortest path matrix, where you're not allowed to use any edge as an intermediate vertex. Notice there is a path of length 2, from 2 to 3. But if we just look at the adjacency matrix, we're not allowed to use that path, right? So in this case, this would be our matrix W superscript 0. The shortest path matrix between every pair of vertices, where I'm not allowed to use any intermediate vertices. Does everybody see that? What Floyd's algorithm does is he uses the numbers of the vertices from 1 to n to define the set of possible intermediaries. What if, in this case, we are allowed to use vertex 1 as an intermediary? Okay? Under what, if we are allowed to use vertex 1 as an intermediary, there is a path from 2 to 3, right? How do we know that there is such a path? If 1 is an intermediary, then what does it mean? If we want to use 1 as an intermediary from 2 to 3, that means there has to be a path from 1 to 2, and sure enough there is. And there has to be a path from 1 to 3, and sure enough there is. Does everybody see that? So, what Floyd's algorithm is he uses this recurrence relation to solve the problem. Okay, let's look at this. Make sure you understand this one. Okay, because we'll talk about dynamic programming later. And this is a good example, next week, in fact. And this is a good example of dynamic programming in action. We're going to say that the shortest path from I to j, using vertices 1 through k as possible intermediaries, is either the shortest path from I to j where you don't use vertex k as an intermediary. Adding that other trip, we want to find the shortest path from here to the airport. If I now allow you to use New York City as a way to do it, that is not going to actually shorten the path, right? So if so, then there is a tour, a path from I to j, using only your previous set of intermediaries. Or, if we can take advantage of using vertex k as an intermediary, the only way would be is if it was cheaper to go from I to k, using at most all the vertices b1 to k, the first k minus 1 as intermediaries, and then a way to get from k to j, using only those same set of intermediaries. Then we could take advantage of this new vertex k as a possible intermediary. Okay? How many people see the recurrence? Raise your hand if you see it. How many people don't see it? Raise your hand if you don't. Yes? Question. Or you don't see it.
The right side, k minus 1 is always smaller than
Well, what this is saying, these are saying, well, no. This is saying, this k minus 1, remember, is the list of possible intermediaries. K here is supposed to be reflecting not a power, but what my possible intermediaries are. This is what the difference is. Make sure you're interpreting it right. So here, I am numbering my vertices. Let's take a look at this graph. I am numbering my vertices in terms of, let's look at a slightly better, simpler example. Let's say that I wanted to figure out 1, 5, 2, 3, 4. Whatever. Something like this. Okay, let's say this is my graph. If I want to find the shortest path from 1 to 5, where 1 is allowed, where nothing is allowed as an intermediary, the shortest path from here to it is, well, there is no. Let's say all of these are of weight 1. All edges are of weight 1. If we ask for W sub 1 comma 5 of 0, is there a path from edge 1 to 5? Okay, using no intermediates. The answer to this is it's infinite, right? There is no such way to do it. Is there a path from 1 to 2 using, 1 to 5 using 2 as an intermediate? The answer is still no. Does everybody see that? Is the answer, if we're allowed to use 2 and 3 as an intermediate, then yes, there is a path of length 3. Does everybody see that? The optimal answer of 2 only becomes true when we're allowed to use this and this and this as possible intermediates. Right? So this is not an exponent. It's a set of what intermediates we're allowed to go to. And basically, I'm the shortest path where I'm allowed to use k in any one of the vertices v1 through vk. Not that I'm allowed to use k intermediates, but I'm only allowed to use the intermediates 1 through k. Basically, this was the shortest path from here to here where I wasn't allowed to use k. This is the shortest path from I to k where I wasn't allowed to use k as an intermediate. From k to j where I wasn't allowed to use k as an intermediate. If I am allowed to use k as an intermediate, the path is going to be from I to k and then from k to j. And that's what this is counting. Do you now buy the recurrence? Or does this still bother you? I respect it bothering you. I'm not trying to... Okay? Any questions about it? Okay, think about this. The nice thing about this program is that if you do it, there is a very, very short, a trivially short algorithm for it. This solves the all pair shortest path problem. Okay? And this is something that, one could easily imagine typing up in a short period of time. Okay? It's better than Dijkstra in that it uses fewer lines. It's better than Dijkstra in that it gives you all pair shortest path. It's better than Dijkstra in that it gives you something sensible, by the way, in the case of negative weight edges. Okay? That this will actually recover from negative weight edges, unless there's sort of a negative cost cycle in it. Okay? And that's where you would get to be, they turn out to be big troubles. Okay? Shortest path's not well defined if you have, if someone will give me money, if after coming through here I have more money than before, I would keep wanting to do this an infinite number of times, right? And then the least expensive trip isn't well defined. The disadvantage of Floyd's algorithm is simply that it is an n-cubed algorithm as opposed to an n-squared algorithm. And so it can be overkill in the case of, when you just need the shortest path from here to there. Any questions about that? Okay? The other problem And as I promised, is all I'll talk about today. The other problem is is a problem called transitive closure. What is the transitive closure of a graph? Has anybody ever heard of that word? Who's ever heard of transitive closure? No one. A few people. Okay? What does it mean? The transitive closure is, given a directed graph, it's a question of who can reach somebody else. Okay? This is what gets into this question of, if I have a directed graph, in a transitive closure, I will have an edge between, if I give you a directed graph like, let's say this to this to this, the transitive closure of it is going to add edges between any pair of vertices that can reach each other. This could reach this one could not reach that one, so that's not going to be in the transitive closure matrix. Okay? So, one thing that should be clear is that Floyd's algorithm can tell me who reaches whom if I set a graph where I said every edge should be of weight 1, the non-edges of weight infinity. I compute the all pairs shortest path. There would be no wedge path between here and here, so it would still be maxent. But any pair of edges that are not, any pair of vertices where the weight is not maxent anymore, there's a way to get from I to J. Okay? Computing this thing turns out to be useful in different applications. Let me just give you one silly application. How many people here are familiar with the crime of blackmail? I know what they call it here. Who's ever heard of the crime of blackmail? Okay? I think here, it sort of, and here I'm extrapolating here. I hear about Edison Chen and the movie stars. Okay? So, in the United States, there's a crime called blackmail, where I will, if I know a bad secret about you, I will say, I will tell everybody this secret unless you do what I tell you to do. Right? Does everybody see that? What do they call that crime here? Do they call that crime here anything? What is it called? Okay? Suppose, let's say, I have a graph where I can blackmail you. If I can blackmail you directly, I have an edge from me to you. Okay? Now my question is, if I want to find somebody to hire to do dirty work for me, who should I hire? Is it the person who can blackmail the most people directly? Like, again, Edison Chen with his photographs of naked women all over the place? Okay? Or was it the guy who stole Edison Chen's computer and had the picture of all the dirty things, right? He could blackmail Edison Chen. Edison Chen could blackmail everybody else, right? So somehow this flow of blackmail relationships, this is actually related to who can I reach from me? And that's related to the problem of transitive closure. Okay, so thinking about transitive closure, there's applications where that matters. Okay, and this is found using shortest path problems. Any questions? Okay, I've rattled on for a while. I won't talk about network flow yet, although I hope I'll talk to it next class if we have the time. Let me just quickly go through the problems. The first problem is a connect the dots problem. You have a bunch of freckles. You want to connect them using as little ink as possible. How do you go and find a way to do that? The second one, the necklace problem, says you're given a collection of bicolored beads. This one's red, this one's blue. And the question is you want to string them up into a necklace with the property that neighboring beads share colors, blue, green. Okay? And we want to find a way to do that, if it's possible. The tourist guide one, okay, asks for a way to, they give you a criteria to identify where there are cameras in a network. And you want to try to avoid the cameras, identify where the cameras have to be, given the property for how they are placed. And we'll talk about that. And finally, there's a problem of seating people at a dinner. with the property that no two members of the dinner sit at this of a team sit at the same table. Okay, and this is a different one. Okay, any questions? Okay, think about this. I'll see you guys on Wednesday, and let's see how far we get on these. Okay, thanks for your attention. I'll see you guys then.